Good morning. Yes, since we're on a bit of a digital theme with NX1, now shifting gears over to GV, the FM space. We've been talking about our GV2 product line for a little bit, but the exciting thing is, well, it's all coming together now. It's getting real. We've got real systems on the air. So let's dive in and explain what it's all about. So our vision has been to create a application infrastructure where we can have all modulation content distributed over IP streams. And it's synchronous and time-locked, and we'll get into that a little bit more in a little bit. And it's a single content stream that takes care of all of your modulation needs, and that allows us to also create backup air chains. In order to do that, we wanted to create an application architecture that allows us to plug in different applications, so to speak. And the very first application shown on here would be our AUI. So we settled on a virtualization engine, and we've chosen the Proxmox platform to accomplish that. And that allows us to bring together multi-vendor solutions. It doesn't matter what operating system they're bringing to the table, whether it's running in a Docker container, a Linux container. We can all bring all these solutions together because we know as Nautel, we do a lot of great products, but we can't do everything. So this is an opportunity for other manufacturers that are working with us to bring the solutions to the table to come up with a single solution that's all running in our transmitter. And that really is creating an ecosystem for broadcast air chains, and that makes it all flexible, scalable, and future-proof. Because we're no longer hardware bound by hardware boxes. It's all software functionality that's all running in our transmitter. So at this point, we've shipped over 100 GV2 transmitters since we introduced the initial offering with that. So those 100 GV2 transmitters would have that application platform built into them, and they all support all the legacy modes that GV brought to the table. So we can still do everything that GV used to do. So we can still do FM modes, FM plus HD modes, HD only, all digital modes, as well as DRM, just like the old GV used to do. But now we have this application platform in there that makes it future-proof, and now we can just load in extra applications and start setting up HD radio without having to install extra boxes, and we'll get into that a little bit more. So we've got 100 of those systems shipped already, but initially they only shipped with the engine. So now we're going to get into the applications that we're starting to support. So the new thing now is that we have the extra applications ready for you to install on the system. So we have VXGen is what we call it, which is the modulator. Get into that a little bit more in a second, and the vPorter, which is effectively the fourth generation importer-exporter. That was released last November, and they're typically a bundle. If you get the XGen app, you also get the vPorter app all installed in the transmitter, so you're ready to go. And optionally, there's also Nielsen encoding in there, and it does all of the audio encoding for FM HD1, 2, 3, and 4. Again, we'll get into that a little bit more detail in a second. So all of the GVs that I mentioned, 100 that I mentioned a minute ago, they can now be upgraded to install these applications. The intent is to you install them using a USB stick that then installs a new virtual machine, spins it up, gets it all configured for you. Some of the initial systems, we might encourage you to replace the hard drive wholesale to make it a little bit easier. But the idea is long-term is you walk up to the transmitter with a USB stick, it puts the application on, and then you can configure it and use it. These GV2s are built in our Bangor facilities as well as in Halifax. And today, 5 systems have already installed these applications and are on air, and 3 more are on their way coming. Now, we're already looking at GV software version 2.0, and that's coming soon. And the reason why we have to do that is it will support a newer, even more powerful SBC compute platform in the system, and that's why we had to go up to a major version just to delineate it. But functionally, it's the same as everything else. It has the XGen and the vPorter built in. So let's have a closer look at the applications themselves. So VXGen, and the little V indicates virtual. So it's no longer a card. We used to build an XGen card with the modular code running on it that's supplied by Xperi. Now it is an entire software module. So there's no cards to install. You load up the software, you enable it, and it's based on latest fourth generation Xperi released XGen code. So it supports all of their latest service modes, the standard ones, the hybrid service modes, MP1, MP3, MP11 that you're familiar with. It does all of those. We can also turn on the all digital service modes, MP5 and MP6. And also new, we showed that last year at the NAB show floor, there's new experimental modes that Xperi is developing, and one of those is MP1XOV. We don't have time to get into those details, but for those that are familiar with HD radio, you see a constellation with 16 data points. Normally, you would only see 4. So it's interesting to play with that. It's probably a little bit early to put these systems on air, but if anybody's interested in doing trials, that's certainly something we can discuss. The whole system is a software platform, but at some point, it has to talk to our hardware transmitter. And we do that using a USB connection that the VXGen application opens up a USB device that we install on our exciter, and it takes the place of what used to be the hardware XGen card. So we replace the hardware XGen card with a USB card, and then the software will take over and can do all the modulations. And the neat thing about this approach is it's really agnostic. We can change the modulator with a different modulator. We could internationally install Digital Radio Mondiale, same thing, just different software. It could just be used for FM only, so it's really agnostic in terms of what the final application is. Now, what we call the virtual B-porter is the fourth generation importer, but it's also, and I'll get into that a little bit more, coupled with an audio processor, the Omnia for Nautel. So the GV2s that are, if that option is ordered with the transmitter, will ship with the transmitter already pre-installed. So it includes the latest fourth generation importer with that. And it's entirely software based. There's no audio capture cards, and there's no need to hook up GPS at all. In our system, the synchronization is accomplished using the internal crystals rather than having to take the signal off air. And we can maintain perfect time lock without having to have a GPS antenna installed, so it'll make the installation a little bit easier as well. And we've already talked a little bit about the value of graphical support in your broadcast. We can even install the QRapid application right on our system as well, and that's what we demonstrated last year. Now, a little bit of a word about Omnia for Nautel. So we've got a full-fledged audio processor in here, and the reason for that is, well, with HD radio, we've got all these extra audio streams. You'll have to think about the audio processing. So we thought we wanted to get a solution in place that makes it easy for the broadcaster to process all your audio, HD 1, 2, 3, 4, all in one match. So we looked at the Omnia 9 platform, and this is what TELUS Alliance offers as a hardware audio processor. Some of you might be familiar with it. And it can do, by default, FM HD 1, 2, 3, and 4. Well, it does 3 out of the box. There is ways, apparently, to get 4 in there as well. But you can see, because it's a hardware box, even the audio inputs and back are limited by the number of channels. Once we get into audio over IP, a lot of these limitations go away. And when we move this code, this core functionality into our transmitter, we can offer HD4 as well. So now, all you have to apply is AES67 or Livewire to the transmitter for FM HD 1, 2, 3, 4. We do all the processing, the RDS encoding, the HD modulation, and, well, it's just add audio. No, it makes it sound a little bit simpler than it is, but yes, adding the audio will get you all the modulation. So just a little bit of a word. So how do we keep it all synchronized? How do we manage to get FM HD diversity delay locked? And ever since we started development, even with the early proof of concept prototypes we developed, there's one number we put in for the diversity delay to match the FM to the HD1. We never had to change it. It doesn't matter if we reboot the system. It doesn't matter if there's any sort of drift in the reference crystals. It is the same delay. It's now fire and forget. So there's no more off-air receiver correction required. But why does it work? Well, we realized that you really have to control the entire air chain from where the audio splits. You know, you have a single studio feed for the FM HD1, it's a simulcast, so the same audio coming in, but it splits the audio processor. You know, the base processing will be the same for both streams to, you know, make it sound the same equalization, you know, the same audio shaping. But at some point, it will split into the FM output, because at some point you have to do a stereo generation. There's final limiters to get you just a little bit more audio output. But for HD, you don't need the stereo generator. It just wants left-right audio. So at some point, there is a split in the system. And typically, if those are different hardware boxes, different solutions, you really don't have control over all the synchronizations for those. That's where a lot of the time slip is coming in. But by us offering it as a single solution, we can control everything. So both the analog path on the bottom and the digital path on the top, even though they take a different parallel path, they get recombined into a single IP stream in the middle here, in such a way that they can't slip no matter what the delay across an STL or whatever the communication path is between those components. It is locked into a single bit stream. But also very important, the modulator on the far end has to be able to take both of pieces of information for the FM and the HD and does the modulation for both components and then joins them back together in the RF waveform that's about to be broadcast. And so by making this a synchronous system where we don't lose any samples, all the rates are perfectly rate locked, and I have a paper that I can share with you for all the details if you'd like, but that's how we can make sure that diversity delay is no longer an issue. So at this point, you don't need an off-air receiver to correct it, and the dangers, even with an off-air receiver, which is part of some of our competing products. They do the auto correction, is even car receivers these days are trying to do their own alignment of the FM and the HD simulcast so that when it blends it's good. So they're doing their own correction. If the broadcast plant is continually adaptively changing the delays to match it as well, the two control loops can fight and become unstable. What some car receivers then do is if they say, oh, I can't really correlate those signals, I'm going to turn off the HD entirely and just produce or only present FM to the listener. So even though you're broadcasting HD, your receiver may not actually have HD in the car because something's chasing delays. So there's very strict guidelines as to how much you can delay. With this architecture, it's a thing of the past. It's a fixed delay. It doesn't change. It hasn't changed in years. You dial it once. It's just a default setting when we go ship the transmitter, and it's not a problem anymore. So what have we achieved towards our vision today? You've got all the apps on the right, and in doing so, by the time you add up all the components you would have to install as discrete boxes, we've lowered the HD radio conversion costs. And a big part of that is to have a cost-effective audio processing solution for all of the HD radio channels. It's a simpler HD radio installation with fewer boxes. I can show you a transmitter that essentially you apply power, you apply one Ethernet cable, and it produces all the modulation content you need. And as I just mentioned, we fixed the diversity delay time lock, and that, again, makes it simpler by not having to install another receiver. But what about the other part of our vision? So now we've got the transmitter fixed, and that's a great solution for many installations. But now we want to have a look and see how do we move a synchronous IP stream that's currently communicating inside the GV transmitter across the entire ecosystem. So let's have a closer look at that. So we've introduced an AirChain MPX plus E2X transport protocol. And if you line up HD radio and your typical FM processing chains, you can kind of see that the Gen 4 HD radio encoder, it has a similar functionality to essentially a stereo generator that creates an FM composite multiplex. In HD radio, it creates an HD radio multiplex. So those functional components are very similar. So by looking at that is, from left to right, from your studio automation, where you have multiple playouts, up to 4 streams, whatnot, feed it all into the audio processing. And then if you feed it into the audio processor for the composite and then the HD radio Gen 4 signal, you can see all the services are all encompassed in this one data stream. So your HD1 audio, HD2, 3, 4, your program service data for all 4, your album art for all 4, your station logo for all 4. So if you think about it, if you wanted to independently put all these streams up to a transmitter site, you're talking about 12 or more connections or streams that you have to manage. Now we have a single pipe that delivers everything in one shot, and that makes it much easier for backup configurations. By the same token, the composite MPX does your left minus rate, your pilot, left plus rate, and your RDS, and potentially even sub-carrier modulation. Again, all of that data stream now has all of the modulation content you want to put on air. And one thing you'll see on our demonstration on the show floor, what that makes it very nice for us, we can even take this data stream, save it to a file, and play it back, and you have the entire broadcast signal, and that's what we ended up showing up at the NAB show floor today. One more important word about transport protocols here. The effect of cascading codecs is something that you have to consider for HD radio. HD radio uses an HD radio codec, which is a precursor to high-efficiency AAC version 2. It's very close to it. But the danger is if you use a transport mechanism that uses a perceptual codec that's then followed on by the HD radio encoder, you can get coding artifacts that pop up at low bit rates. So in this architecture, there's only one audio encoding. From the PCM, the raw audio, professional grade audio at the studio, there's only one encoding that's happening in the Gen 4 system, and it creates the bit stream precisely the way the HD radio receiver at the far end will pick it up. So there's no transcoding in the entire transport stream, and the bits are encoded with the 24 kilobits that the HD radio stream, or whatever bit rate you choose for your channel over the air, it matches that precisely. So no transcoding and all of that. So a word about the distribution with this now. Let's unpack this. It's a pretty busy slide here. We need to unpack that a little bit. So again, on the right-hand side, we have the 3 apps I've already talked about. And that transport protocol currently, if in your GV2, is running within the vPorter and the VXGen. It's just running internally. But if we moved it to the outside, so first let's have a look at, let's assume, look at the data center case on the bottom right here. We can move the vPorter application from the GV2 into your own data center that your own IT department manages. We can have it running in there, and it will then send that MPX to E2X data stream to the GV2 transmitter. And now we can have all your live wire inputs at your program origination in the data center, at the studio, wherever it makes sense. And you don't have to think about how to get all of that audio up the mountain. So now it's all on your premise data center. If you have 2 or more IP connections, 2 or more IP providers, maybe you have a fiber link and a copper link, maybe a satellite link. We can use multiple links to create a hitless failover, and we've demonstrated that at NAB, where it's able to disconnect one Ethernet cable, plug it back in, disconnect the other one, and it's hitless. There's no impact on the on-air broadcast. The HD radio receiver stays locked. The FM sees no difference. It can simply switch over between one or the other. So those are the bottom 2 streams here. Because we've taken away all of the hardware requirements in the vPorter, it's entirely software, well, you can run it in a public cloud infrastructure as well. And we've demonstrated that a few years ago with a demonstration where we moved the vPorter from an Ohio data center in AWS down to Sao Paulo, Brazil. And the diversity delay, like I mentioned earlier, always lockstep. So it doesn't matter where you're running, and so it becomes agnostic. One more point on that is the vPorter can also be fanned out to multiple destinations. So if you have translators or in an SFN application, one vPorter can also split out. So not only can you have multiple vPorters feeding one transmitter, but you can also fan it out to multiple transmitters in a fleet or a network. But keep in mind, the vPorter is what controls your broadcast signal. So that only works if you want the exact same signal on air on both transmitters. It could be an aux site, it could be a translator, so that's certainly a possibility. Also part of the story, and we demonstrated that at a previous NAB, is emergency alerting. Now in this architecture, we actually have two EAS insertion possibilities, and we have to get away from this inline audio cut-in concept here. With audio over IP and audio routing, it becomes much easier to insert. And the first thing that we offer is in our Omnia for Nautel, you can have a dedicated EAS live art channel, and if that channel is active, it will break into HD 1, 2, 3, 4 automatically, and that handles that. So that's one insertion point. So you can have an EAS unit like Digital Alert Systems DASTEC, and that was our demonstration that we did, and it could either communicate to a playout system to do an orderly insertion of something like a weekly test. So that's one insertion point to do that. But the other insertion point is we can switch entire air chains. Let's say the data center vPorter on the left here is your 24/7 programming. And other than sort of the weekly test, it never really knows about EAS per se. But if the link fails and your transfer becomes an island, we can have a dedicated air chain just for EAS on the right-hand side. So therefore, even if all else fails and you're the last communication link, you can get on air and have all your EAS information on air locally. Because of this software approach, we can clone these components quite easily. What we also demonstrated with that approach is in this particular instance, we picked 4 symbols, graphical symbols, and that are in common use across the TV industry, and put those on HD radio. And you can see there's a picture of a BMW motorbike that showed the tsunami warning. It kind of pops up quite nicely. But the key thing for a broadcaster notice here is after the EAS audio insertion, we can keep graphical and textual content over HD radio, inform the general public while the audio goes back to regular scheduled programming. So we can continue to warn about hurricanes or weather warnings and while the event is active, perhaps with periodic cut-ins, but for the main duration, you can go back to regular scheduled programming. So that's, and we won a couple of awards with this demonstration a few years ago. This architecture makes that possible. Another solution that we want to highlight here is a common use case for HD radio today is the use of an analog FM translator that is listening to an HD 2, 3, or 4 broadcast and then rebroadcasts it as analog FM, not as HD radio, not digital, but as analog HD radio. So one of the key things that we figured is how we can reduce or the system complexity with that is our Omnia for Nautel has built-in audio encoders. So we can take an HD2 stream that's already processed as part of your main transmitter, and we can send it over IP to something like a small VX transmitter into its audio player, and then have it do the stereo generation final limiting as part of that system. And it could either be PCM-based AES-67, it could be the free lossless audio coder FLAC, or it could be micro MPX. But it has to be a codec that preserves the limiting that we do in the main transmitter. And in doing so, by coupling your main broadcast GV2 with your translators, we can come up with a simpler system implementation for those use cases. So your GV2 will help your analog translators in this sort of configuration. We think that would make it certainly an easier implementation for HD radio translators. You still legally need to have a receiver listening to your main station, but we recommend that it's probably best done using an external HD radio receiver, because the location where you install your transmitter may not be the best location to pick up the main station's signal to listen to. And there's a lot of great products in the market. I believe Innovonics is bringing a few to the market, but there's also other solutions. So, check them out for those sort of solutions. But with this architecture, I think we can do all of that. So in summary, we're now shipping GV2 with those HD radio components. Come see it on our booth. And there's an upgrade path for all GV transmitters, even from the very first ones, up to GV2. And it's simple to just add audio once you're there. And it's a low-cost HD radio conversion with all of the audio processing in the GV2. And now what we're looking at next is looking at this distribution solution, so we can really build a whole ecosystem of broadcast applications talking to our transmitter. So that will help with centralized fleet management, and we're hoping to offer this up as an industry standard with the NRSC, IEEE. So we would like to see an ecosystem of other vendors being able to participate in that ecosystem as well. So come to our demonstration on our booth, C2546, and what we're showing this year is the GV2, of course. But what we've done is we've taken 3 real stations, recorded their signals that they're broadcasting over the air. We've recorded it live and then brought it to the NAB show floor as files, and we can switch between the different stations, and you can see what they've done with this AirChain HD radio installation. So in the message, it's no longer a science experiment. It is out there. We're building out systems. And of course, there's always new innovation that we're going to push as we're moving along here. So that wraps it up for my portion here. I'll pass it back to John White.